Hello, and thank you for tuning in to Connections and Directions, our University of Michigan Civil and Environmental Engineering podcast. My name is Michelle Santillan, and I am the CEE Marketing Communications Specialist and host of this series. During our podcasts, we are featuring members of our CEE community and how their work reflects our mission of engineers in service to society. We will be highlighting our strategic directions and our commitment to diversity, equity, and inclusion. CEE's 5 strategic directions are human habitat experience, shaping resource flows, adaptation, automation, and smart infrastructure finance. Our guest for this podcast is Professor Evgeny Filipov. He received his bachelor's degree from Rensselaer Polytechnic Institute and his master's and PhD degrees from the University of Illinois at Urbana-Champaign. Professor Filipov's main research interests are in the field of deployable and reconfigurable structural systems. Folding and adaptable structures based on the principles of origami can have practical applications ranging in scale and discipline from biomedical robotics to deployable architecture. Professor Filipov, thank you for joining us today.
Hi, Michelle. Thanks for having me on the podcast. This is really exciting.
Please share with our listeners some details about your research area and goals and how they align with CEE's strategic directions and our mission of engineers in service to society.
All right. Well, to talk about my research, it's probably easiest to start with talking about some of the applications. So again, I'm working on this somewhat different field of folding structures based on the principles of origami. And it's a good idea to think of maybe some of the applications that we can have in engineering. The field really started off with space structures. And when you want to launch something in space, you want to have it really nice and compact and small to put in your rocket. And then once you get into space, you want to deploy it. And a good example is the solar arrays. You really want to have something compact, put it in space, and then maximize your surface area so you can get a lot more light on your solar arrays. But the same principles work here on Earth as well. So imagine you may have a deployable bridge, and after an earthquake or some other disaster, you lose a bridge, and now you don't have access to that area. Well, if you have a deployable bridge, you can deploy it very quickly, you can have it on site, and you can restore access on that road and get people goods, get them to the necessary resources, get them to a hospital. So these same principles of deployability apply to our structures down here as well. Another example would be shelters, right? After a disaster, maybe you lose a lot of shelters and you want to have people restored and have a safe place to live quickly. And so you could have these deployable systems that are pre-manufactured and ready to deploy on use. Another idea could be in areas where you have a very constricted environment. So if you're building in the downtown Manhattan and you want to build something quickly, it's difficult. You have a lot of logistics that are difficult to manage. You have to close a lot of roads. It's a very expensive place to build. And so if you could have parts of your building pre-manufactured in some location farther away, you could have the walls, the windows, the doors, maybe even your furniture that are folded down onto a pallet. You have many of these pallets on a truck, drive them down to New York City, and a crane will lift each one up and pull it up open and have everything deploy in your structure so you're rapidly constructing in this type of restricted environment. Or the same for a difficult place to reach, whether you're trying to build out in the desert or on the moon or on Mars, these same principles of deployable structures are really valuable. So now to get into some of the details of what my work really is, I work on the deep fundamentals of these types of folding structures. So I work on the structural mechanics, which means looking at how they behave when you apply a load onto them, how they deform, and how they really function. So I build analytical models that allow us to understand these structures, that allow us to simulate how they're folding, how they're moving, what happens if we apply a load onto them. And some of our work has really focused on how do you make these folding origami structures, these really thin structures, to actually be stiff enough to take loads. So when you have something like origami, it's a flexible sheet, so it wants to deform in a lot of different ways, and it's really flexible. And from one part, you want that. You want this structure to be easy to deploy and to open up. But at the same time, once it opens up, you want that structure to be stiff to really carry loads. And what we found is there's really neat ways that you can arrange the way these sheets are folded. You can put them in a strategic fashion and build structures that now start to have a very high stiffness. So we've been able to create beams, columns, different types of dome shapes, different types of corrugations that have these really nice properties of being deployable, but at the same time being very stiff when you want them to be stiff. And so many of the examples that we have in our lab, our simulations and our experiments show that, even though they're made out of really thin sheets, they can support many times their own weight. Often thousands times their own self-weight, without really seeing a visible deformation. So that really allows us to think, yes, this is origami. These are thin, flexible sheets. But if you arrange them in the right way, you can really have stiff structures that you can use. Another of these kind of fundamental challenges that we're trying to overcome is actuation. How do you actuate these structures? How do you make it easy to actuate? And specifically, if we're thinking about applications here on Earth, one of the big challenges we have is gravity. These deployable bridges or buildings will be quite heavy, and so we need to overcome gravity. How do you deploy with respect to gravity? And so some of the ideas we're working with now are to have counterbalances or counteracting gravity in different ways. So what we have are pre-stressed springs inside of our structures. And so as our structure is deploying, these pre-stressed springs let off force, and they allow the structure to deploy without us having to use these really big actuators. So we have a very efficient way to deploy the structures. And again, we work on other types of fundamental issues. So how do you manufacture these? How do you fabricate them? What materials do you use? And our work is really becomes quite broad. You can apply these same principles to space structures, to civil engineering structures, to robotics, and to all types of systems. So just as an example of some of the projects we have in our lab right now, we're looking at meter scale structures, again, for civil engineering applications. We have one project looking at deployable boats, so you can have a boat that rapidly deploys when you need it, and it will change its shape and its hydrodynamic characteristics. We have a project looking at microrobotics. So this is our collaboration with the mechanical engineering department with Professor Oldham there. And what we're doing there is we're using the same principles that you would to fabricate microchips, basically the chips we have in our smartphones. You put many layers of material, and then we use origami principles, these same ideas, to fold them up and to construct micro-scale robotics. So these are robots that are about 1 to 5 millimeters in size. But again, the fundamental principles and the fundamental challenges there are very similar. You want these to be very lightweight robots. You want them to be stiff and to be able to achieve their functions. And you want them to be easy to actuate so you can move them around and accomplish different tasks. And so these robots could then ultimately be used for sensing, for inspecting if you have damage in your buildings and structures, or a lot of other uses as well. Now, related to the strategic themes in our department, as you mentioned, one of those is adaptation, and I really see my work closely aligning along with this theme of adaptation. So basically, the premise of the theme is that, right, we as a society need to think of how our systems and our infrastructure adapt to the many new challenges that are emerging today, right? Increasing hazards, climate change. And I really see that the deployable structures are, in a way, adaptable structures. So we talked about, recovery after a disaster and so on. But even a more direct example could be seawalls. A lot of communities around the U.S. now are starting to look at seawalls in defense of hurricanes and other types of disasters. And if you have deployable seawalls, we can be a little bit more strategic about how we think about using them, right? In the U.S., when we have a hurricane, it's usually going to be in one location that it's going to strike. So we can have prefabricated seawalls that are packaged and ready to go. And whenever we expect that there's going to be this high flood risk, we can go deploy them strategically to control the flooding. And then after the use, pack them back up, and then our beach becomes usable again, so we can use it like we always did before. And many of these deployable structures also have these adaptable characteristics. So when we think of our buildings and our facades, for example, most of our building facades today are static. We have our windows, we have our walls, but they don't really move. They don't really have this ability to move. And so if we build in these principles of folding and adaptability into our facades, they can maybe adjust their shape depending on the time of day, allow more light or heat to come in depending on what our temperature is, so we can be more comfortable in our buildings. Or we could even have walls within our buildings that move and rearrange so we can reconfigure the space that we're really using and use it more efficiently and in a better way. So I really see that my work kind of works quite well with this general theme of adaptation for a modern society.
And given, as you were just saying about the hurricanes, for example, are you aware if any of these type of deployable structures have been implemented down in Florida, for example, where bridges may have been washed out and there's a need for access to islands or other areas?
Yeah, so unfortunately today there aren't so many applications out there. The principles are being used and they have been used somewhat already. So if you think about concert venues, the stages that they use for concerts, they often use origami principles, and we have some of this. But right now, for example, in Florida, there probably are being delivered some types of deployable shelters. If you even think about a tent, that's in a way a deployable type of structure. So there are some uses, but one of the challenges is they're not widespread. The current principles and methods are very expensive, and it's not easy for us to build many of these structures, these seawalls that we're envisioning. There aren't really many of those out available yet. And so what our work really tries to do is, can we solve some of these fundamental problems to make them more cost-effective, more functional, easier to fabricate, easier to make, more durable at the same time, easier to actuate, again, is another issue. So if you are in type of a constricted environment, you want it to be easy to actuate when you maybe don't have access to cranes and other types of infrastructure to actuate. So we're really trying to solve these fundamental problems, and our hope is that, yes, in a few years, we'll have a lot more of these types of structures available and ready to use.
Mm-hmm. And how did you first become interested in studying origami structures?
Yeah, so this is actually a very interesting question, and it's not a very traditional path that kind of led me to this. So my bachelor's degree and most of my early work was very traditional civil engineering. I did my bachelor's in civil engineering. I was interested in buildings and structures. And into my master's, I was kind of kept the same interest. My master's was focused on seismic risk of bridges, so earthquakes and how bridges behave under earthquakes. And I started modeling these bridges and how they deform and how they shake and so on, basically what are the effects that earthquakes have on them. And then as I started my PhD with my advisor, we kind of got excited about the potential of this area of origami. And back then, this was 2013, 2014, there really wasn't anything out there. There weren't really many of these ideas that we're even talking about today. And most people would really see origami as a toy, but we really saw potential of it, and we got really excited and wanted to learn it. And at the time, there wasn't really many people that were looking at origami as a structure. So to really envision it, can you really use it as a structure? And actually, it was quite neat that the same tools and equations and models that we're using for buildings and especially looking at bridges and how they shake under earthquakes became really relevant to actually studying origami as structures. And so we started studying origami more as structures. I got to go work in Japan for 6 months with really somebody who I'd say is an origami expert. They really understand the principles of origami. A great collaborator, Tomohiro Tachi, he really understands, kind of the basics of origami, the fundamental principles there. But we came in with our structural engineering background to really kind of combine these two fields. So we get this idea of folding and deployability, but then really bring in realistic structural mechanics principles to back it up and really convert these into functional, like I said, stiff and lightweight structures. So yeah, that's not really a traditional path of how you might find a research topic.
And what are some of the classes that you typically teach here at U of M? Do you bring origami into some of your coursework?
Yeah, I do. I actually have a class that's really focused on deployable and reconfigurable structures. So I have a graduate class where our students learn about the basics of folding, and we talk about all types of deployable structures, from more conventional systems to all the way to origami. So we talk about the fundamental principles. We learn these simulation tools that I was talking about, how to use them, and the fabrication methods, the actuation, more practical aspects related to design as well. And it's a really exciting class. There's a class project that we have, so about half of the class is based on projects, and the students get to design really what they want, something related to deployable structures. And we've had many of these applications that I talked about. They've done designs and small-scale prototypes of deployable seawalls, shelters on the moon and Mars. There's been bridges. But the class is open to the entire College of Engineering, and so we often get students coming in from mechanical engineering and aerospace, biomedical engineering as well. So there's been applications in robotics, metamaterials, kind of novel material systems that use origami. And one that was really exciting was medical implants. So somebody was looking at, can you make these medical implants that you have to make a small cut, you put it inside your body, and then it will deploy inside. So just really neat projects that the students get to do that are quite well aligned with what their interests really are.
In some of the ways that you're describing, I almost envision a Slinky toy as part of that deployability. Does that come into play at all?
I haven't looked at Slinkies, but I bet you that we could find a pretty neat research problem that relate to those. Yeah, many of them do behave in a similar way. They're just easy to pull out and easy to deploy. What we can provide then is then they get really stiff at that deployed state, so a little bit different, but yeah, cool things.
How do you incorporate diversity, equity, and inclusion into your research and courses?
Yeah. So related to my research, origami is really an accessible subject, and so it's accessible to small children, to adults, to really the broad community. So we find it as a very good way to communicate what we're doing here in engineering to the public. So what we've done with my research group is we have a few events where we'd go out either to local libraries, or we've done this at a few high schools around here as well, where we go and present our work. And we let basically the students in the community work with origami, play with origami, and build their own models. And at the same time, we demonstrate, you can fold these thin sheets and you can ultimately make structures that really have these emerging new types of really exciting applications. So it's a really neat way to show students that, yes, you can have these art forms and you can have something that's really exciting, that's kind of like a toy, but this is really practical and really relevant to engineering. So we think this is a great way to engage younger students of all types into engineering and get them excited about coming and becoming engineers. Another thing that I do through my classes, and I've kind of started this a couple years after I started here, was I introduced this module in my classes that I call Engineer of the Week. And I have done this for some of my classes. And the starting point of this was, we have these books, and I was mentioning I teach a fundamentals class on deformations of material and structures. And the principles we cover in that class were, some of them were, discovered and invented 300 years ago, 200 years ago, 100 years ago. They're really kind of basic, really fundamental principles. And the book talks about them, but unfortunately what ends up happening is they also talk about the people that invented them. And unfortunately, all of those were, white, male, often people of European descent. And that's not a very good reflection of who engineers are today. And that kind of was a shock to me. I'm teaching this to my students, but this is not really what engineering is today. And so what I decided to do is that every week in my class, I feature an engineer of the week. And so some weeks I feature these traditional figures, and one of them that I find really exciting is Stephen Timoshenko. He was actually a professor here. He's developed some really cool things, but again, this was about 100 years ago that he was a faculty member here. And of course, I feature his work, and I say, hey, we're learning this. It's really relevant. But other weeks I feature engineers today that are, they're making great inventions and discoveries today, and they're often women, people of color. They're my colleagues that we're working together with to discover and invent some of these things. So it's really a way that I find that, I can show my class, it doesn't really matter who you are. You can be a great engineer and you can make a contribution to the society. We are inventing these fundamental principles today. It's not just what happened 300 years ago. It's still happening today. Yeah.
Is there anything you would like to add?
Yeah, I guess as a general message to the CE audience, and I guess our CE students in particular, maybe just look for exciting things to do. Just make sure you're doing something excited and that you're passionate about. And keep your mind really open. You never know when something non-traditional, maybe origami or something else that doesn't seem to have a cool engineering application today, might really have a good application and a good purpose one day. So keep your mind open.
Thank you, Professor Filipov, for joining us today.
Thanks.
Thank you for listening to our podcast conversation. For more information about CEE at Michigan, please visit our website at cee.umich.edu. You can also reach our YouTube channel and Facebook, Twitter, Instagram, and LinkedIn pages from our website.